Hi, I'm Sachin from the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. In this tutorial, we will discuss the design considerations for a power converter, an essential building block in many electrical systems. The structure of this session is as follows. First, we will look at the various parasitic elements that influence the switching behavior of semiconductor devices. Next, we will study the operation of commonly used gate driver circuits. And finally, we will conclude with some best practices for PCB layout design in power converters. Let's begin by understanding the parasitics that influence switching behavior in a half bridge circuit. At the heart of any DC motor drive lies the power converter, which typically consists of two half bridges. Each half bridge is formed by connecting two switches S1 and S2 or S3 and S4 in series. By combining multiple half bridges, we can realize a wide range of power converter topologies, from simple buck and boost converters to more complex structures such as LLC resonant converters, dual active bridges, and three phase two level converters. Hence, understanding the design aspects of a single half bridge is critical. To a beginner, a half bridge may appear simple, but to an experienced designer, it hides several parasitic elements that, while unavoidable, can be carefully managed to minimize their negative effects. For clarity, we will group these parasitics into two categories: layout dependent parasitics, shown in the middle of the slide, and package dependent parasitics, shown in the figure on the right. Let's first discuss the layout dependent parasitic inductances. The elements LDC plus and LDC minus represent the inductance of the traces connecting the DC link capacitor to the half bridge. LD and LS are the parasitic inductances near the two switches, while LGG and LSG are the inductances in the gate drive loop. The inductance between the DC link capacitor and the switches, that is LDC plus and LDC minus, can be minimized by placing the decoupling capacitor as close as possible to the half bridge. Doing so confines high frequency current loops to a smaller physical area, thereby reducing inductance and improving switching performance. Another effective technique to reduce parasitic inductance is to use parallel plate conductors for current flow. In a traditional coplanar layout, the forward and return paths lie on the same plane as shown in the figure on the right. This configuration leads to higher inductance, especially when the trace width increases. In contrast, with parallel plates, inductance decreases as the trace width increases, making this method preferable in high power designs. Now let's move on to the package dependent parasitics of a typical MOSFET. These include the inductances of the bond wires and the internal package capacitances as illustrated in the figure. Semiconductor devices are available in many package types: modules, which may contain several switches in a single housing; discrete devices with one switch per package; and integrated solutions, which combine control and power elements into one device. Shown here are two common package types: TO2474L and TO2637L. The TO2474L is a through-hole package with relatively long leads, while the TO2637L is a surface mount package with much shorter leads. As indicated in the table, the loop inductance of the TO2637L is significantly lower than that of the TO2474L, making it more suitable for high-speed switching applications. Let's now turn to the parasitic capacitances within a MOSFET. The gate to source capacitance (CGS) governs how quickly the switch can turn on and start conducting current. The gate to drain capacitance (CGD) influences how fast the voltage across the device changes during switching. And the gate drain to source capacitance (CDS) determines how much energy is lost during hard switching, since the energy stored in this capacitance is dissipated each cycle. Now that we have reviewed the main parasitics in a half bridge, let's move on to understanding how to drive the switches effectively. This figure, taken from a Texas Instruments gate driver datasheet, shows a typical gate driver circuit. Let's examine its main parts. On the left side, we have the control circuit, and on the right side, the half bridge output stage. These are separated by an isolation barrier. The control side receives low voltage PWM signals from a controller, such as a microcontroller or an FPGA, and is powered via the VCC pin. There is also a DIS pin which disables the output in case of a fault. Furthermore, the dead time between the switching of the two transistors or MOSFETs can often be adjusted via an external resistor connected to the DT pin, a useful feature that enhances converter safety. On the output side, each transistor gate is driven by a dedicated circuit. Here, the turn on and turn off gate resistors, denoted as R on and R off, play a critical role in controlling the switching speed and managing electromagnetic interference. The secondary side of the gate driver may use separate isolated power supplies for each switch. However, when cost or space constraints exist, a bootstrap arrangement can be used, requiring only one isolated supply. Keep in mind, though, that this approach limits the achievable duty cycle range. Finally, let's discuss some good practices in PCB layout for power converters. For high frequency designs, typical operating in the tens of kilohertz and above, it is advisable to use at least a 4-layer PCB. This allows a solid layer stackup, for example, signal power traces on layer 1 and 4, and ground planes on layers 2 and 3. The loop area of high di by dt currents should always be minimized. This means that critical components, such as the switches, decoupling capacitors, and diodes, should be placed close together. However, this compact placement must never violate the required clearance and creepage distances for safety. Bypass capacitors should be placed as close as possible to the devices they serve, and the ground plane should remain continuous beneath the high speed signal or power traces to ensure a low impedance return path. To summarize, in this tutorial, we explored the causes and mitigation of parasitic effects in a half bridge, studied a typical gate driver circuit and its key design parameters, and reviewed best practices for PCB layout in power converters. That concludes this tutorial. Thank you for your attention, and I wish you success in your further studies.